a particle is thrown upwards into the air from an origin O. The position vector p with respect to O after t seconds is r is equal to 4ti plus 25t minus 5t squared j meters. Find the velocity vector and the acceleration vector for p, and hence the magnitudes of the velocity and acceleration when t is equal to 4. Determine the Cartesian equation of the path of the particle. Right, before we get into this, just going to look at this using this Geogebra app. So here we have the path of the ball, okay, and if I move this, we can see that's the ball being moved. You can see it moving across there quite easily. So let's put it back here to begin with. So here we have the I direction and the J direction. I prefer to use matrices as for representing my vectors. So if I just click here, okay, at the present time it's on the origin, so the velocity will be 0, 0. If you put t as 0 here, you will get 0, 0. Then as it moves along, you can see, particularly when it sort of gets to t is 2, for example, you can now see this represents the position vector. So it's how far I go along the x, which is 8 in this moment. You see if you put t in there, 4 times 2 is 8. And if we put 8 into 25t minus 5t squared, we're going to get 30. So this line here represents the position vector. So it's an attempt to write things in terms of vectors. Now, if we want to get the velocity vector, well, we know from our work on kinematics or variable calculus that variable acceleration, if we differentiate that, we get 4, and if we differentiate this, we get 25 minus 10t, and this will give me the what's known as the velocity vector. Okay, so here we have the two components of the velocity vector, which is going to be, this one is 4 and this one is 5. If we put t as 2 in here, you can see we're going to get 5. Okay, this one in this component is always going to be a constant. This one is going to change. Now you can think why, physically why it's going to change is because of that the gravity is acting on it and it's going to slow this ball down. And we'll look at that when we look at the acceleration. Okay, and if we move t along, we can see at this particular point there is no vertical velocity. Sorry, I'll just put it back. Sorry. Okay, here we have no vertical velocity, but we still have 4 here. And then after this point, the velocity is acting downwards because the ball is actually falling back towards the ground. Okay, so we can split the velocity into two components. If we just go back up to here, at 1.5 for example, this line here represents the actual line of the velocity at that moment, and the length of that line will give me the speed. And you get the speed from a vector by doing square root of 4 squared plus 10 squared at this particular moment. So we can now see two things. We can see the position vector and the components of the velocity and the actual velocity. Now, if we differentiate this again, this is going to be 0, and if we differentiate this again, we're going to get minus 10. So in fact, the acceleration is independent of t, and we can see, probably the reason is that gravity is roughly 10, and we can just see that A always acts downwards. If I cancel the other two, you'll be able to see that all the time. A is always going to be the same because it's acting against the ball like that. So you can see what's happening here. Okay, so you can, this Geogebra Applet I will put in the notes of the video. Now, it's possible from the displacement vector to find the equation of this path, and that will be that, and I'll show you how to do that in the last part. Okay, so going back to the problem, so the vector r is called the displacement vector, or we can consider it as the position vector. The velocity vector we can get by differentiating r, the r vector, with respect to time. and then you can differentiate the components with respect to time to get the components. So dx dt, dy dt. If you want the speed, then all we need to do is find the magnitude of this vector. Acceleration, surprisingly enough, if you differentiate the velocity vector with respect to time, you will get the acceleration vector. So that means that you would have to differentiate the displacement vector twice, or you need to do d squared x by dt squared, and the same for y. And of course, if you want the magnitude of that, then you just find the magnitude of that vector. So it doesn't mean you need to know how to find the magnitude of a vector and what it means. Okay, so going to our problem. So we've got 40i minus, sorry, it should be plus. Plus 25t minus 5t squared j. So r I like to write like this: 4t 25t minus 5t squared. If you prefer to use this, you can. I just prefer to use this. Okay, so that means we have to differentiate each component. The differential 4t is 4, and the differential of this will be 25 minus 10t. The acceleration means I need to differentiate this again. So if I differentiate 4, I get 0. And if I differentiate this, I get minus 10. So I use minus 10 because it's very close to gravity, although we use minus 9.8. Okay, so note here that the acceleration is a constant. So it's going to be minus 10, so 10 acting downwards. So the magnitude of v is speed. So if we want to find the magnitude, we need to find the magnitude of these vectors. It's 4 squared plus 25 minus t all squared. Might be a good idea to put t is equal to 4 in first. So get the magnitude is the square root of 4 squared plus 25 minus 10 times 4 all squared. So that gives me 4 squared minus 15 squared, which gives me 15.52 meters per second, or 15.5 meters per second. For the magnitude of the acceleration, then we don't need to worry about t being 4, because it's always going to be 0 squared plus 10 minus 10 squared, which is 10 meters per second squared. Okay, the minus sign just means it's acting downwards. So let's just look at that situation on this Geogebra app. So we'll go to t is equal to 4. Okay, so we've got the acceleration acting downwards here. We've got that component acting downwards there, minus 15, and this component being 4. Okay, so now to do the last part, to find the equation of the motion of the particle. So we've also got the acceleration here at minus 10, or just 10 acting downwards. So doing the last part, so note the acceleration in this case is independent of t, won't always be, i.e. a constant. So if r is 4t, 25t minus 5t squared, then the x component of that is 4t, the y component is 25t minus 5t squared. So I've got to try and find the equation of motion. So what you do, you take from this one. So from 1, equation 1, t will be x over 4, and you just substitute that into 2, and that will eliminate t. So we're going to get 25x over 4 minus 5 times x over 4 all squared. So that gives me 25 over 4x minus 5 over 16x squared. Now we would expect this to be a quadratic and with a minus sign because it's sort of that sort of shape. So just one last look at the Geogebra Applet. So that shows us what's happening each time. Like I said, this Geogebra Applet I will put in the notes of the video for you to play with. I hope you've understood, and I thank you very much for watching.